All right, yeah, so Saikat and I will be diving deep into some of the benchmarking and scalability testing we've been doing with Ray on Kubernetes in a single GKE cluster with 10,000 nodes. So quick intro, I'm Andrew Saikat. I'm a software engineer at Google working on GKE. I help maintain KubeRay and have been working on Kubernetes since 2017.
Hi, I'm Saikat. I work in the GKE AI data team dealing with data loading problems at large scale.
Yeah, so first, kind of a quick intro to GKE for folks that may not know. GKE is Google's managed Kubernetes service. One of the most compelling reasons why customers choose to run their workloads, their AI workloads on GKE is that it provides a unified platform for all their AI use cases, from hosting interactive notebooks to training and fine-tuning models, and to large-scale inference with Ray and VLLM. GKE's strength as a platform is that it's very flexible, portable, and scalable. Since the earliest days of Kubernetes, Google has been leading various initiatives to push the boundaries of Kubernetes within Google's compute infrastructure. And the demand and growth of AI has really put GKE's scalability to the test. For example, training the largest and state-of-the-art models requires massive computing power distributed across large clusters that contain tens of thousands of hardware accelerators. GKE provides the orchestration layer to seamlessly manage compute with support up to 15,000 nodes in a single cluster to train the largest models. GKE also supports more than 50,000 TPU chips training a single machine learning model, which we believe has been used to run the world's largest distributed training job for LLMs across 50,000 TPU v5e chips. And in the last year alone, GKE has seen explosive growth of AI with usage of GPUs and TPUs growing more than 900% in a year. And it's no surprise at Ray Summit that really popular option for large-scale distributed computing on GKE is with Ray. So Ray and GKE, they pair really well together because Ray provides the libraries and abstractions for massive parallel computing, and GKE provides that underlying scalable orchestration and infrastructure for computing. The most common way to deploy Ray on GKE today is with KubeRay. KubeRay provides declarative APIs to build machine learning platforms on top of Ray and Kubernetes. It takes advantage of all the great scalable things we love about Kubernetes, like the controller pattern, and it provides highly available and scalable deployments of Ray clusters out of the box. It also provides a great amount of flexibility and customization, which is really important in this rapidly changing AI landscape. So yeah, we're seeing significant growth of Ray and KubeRay on GKE. To support this growth and ensure the optimal performance of Ray on Kubernetes, we start to explore the scalability limits of Ray on GKE. Our focus is on identifying and removing bottlenecks and ensuring that Ray can fully take advantage of the scalability of Kubernetes for highly distributed computing. In our tests, we focused on basically two use cases, one with Ray data, one with Ray train, since these are the most common libraries enabling highly parallel task execution with Ray, and they can also be used for CPU-intensive tasks, which is important for us because it would be really challenging for us to get quota approval for 10,000 GPU nodes. It'd be really expensive. In our testing, we identified 3 dimensions of scalability that were kind of most important for Ray. First is simply the underlying compute infrastructure and orchestration of that infrastructure. This is where GKE's ability to scale to 15,000 nodes and the reliability of the underlying compute through Google Kubernetes Engine is key. Next is efficient capacity management of Ray at large scale. This is where we integrate with Kueue, a very popular Kubernetes native job queuing system. And then lastly, it was ensuring fast parallel data access across thousands of nodes. For this, we leveraged GCS Fuse and Google Cloud Storage. So yeah, let's start with some scale testing we did with Ray Data. As many of you know by now, Ray Data is a scalable data processing library for machine learning workloads. It's really popular right now for batch inference and data processing, and highly efficient and performant at distributed processing of very large data sets. To really stretch the limits of Ray Data, we started searching for a sufficiently large data set to perform a set of benchmarks. We wanted to find a data set that is like really large, and that the big data set needed to be public, so we can kind of publish the results, any reproducible steps for other people to try. One data set we discovered was the Landsat data set. So Landsat is an ongoing mission of Earth observation satellites. It provides the longest continuous space-based record of Earth's land, dating all the way back to 1972. The Landsat archive contains petabytes of data, which translates to millions of individual images acquired over decades. And thanks to the open data policies of the United States Geological Survey and NASA, this data set is available on Google Cloud Storage. So the Google Cloud Storage bucket hosting this data contains approximately 4.5 petabytes of image data. For our use case, we focus on the Landsat 8 collection of images. So the Landsat 8 mission is the 8th satellite in the Landsat program, and the 7th to reach orbit successfully. And for our testing, we chose Landsat 8 because it's the latest completed data set with the highest resolution of images. And it actually contains most of the data of the data set, which is approximately 3.3 petabytes of data. And the image on the right here is an example image from the data set over Salt Lake City. This is the data set structure in the Google Cloud Storage bucket. The first two parts refer to the Landsat satellite and collection number. Those are fixed for our tests. Third and fourth parts refer to the path and row of Earth's surface based on the grid system used by NASA for this data set. And the last part refers to the unique scene ID based on the time the image was taken and various other factors. And then within each scene ID is a collection of images in GeoTIFF format. So our goal is basically to process the entire Landsat 8 data set using Ray Data and KubeRay and on GKE. The job involves basically reading the images, applying a series of torch transformations, such as like resizing the image, converting the data type. And we also open source like all the source code and the Ray job configuration we use in our testing, so it's available in the KubeRay repo if you're interested in the details. So naturally, the first thing we tried was we just said, hey, let's deploy really big Ray cluster, just like one big Ray cluster, and try to have it just process the whole data set. And I shared in kind of the other, in the keynote and other talks, we know that Ray right now supports up to about 8,000 nodes in a single cluster. So the main downside with running such a large Ray cluster is that failures and exceptions or errors are expensive to recover from. So like if the Ray head goes down, like all the GCS data is lost, and then you have to sometimes like recreate the entire Ray cluster. And this is really expensive to do at the scale of thousands of pods. So to fully optimize for the scale that GKE can really support in a reliable and fault-tolerant way, we leveraged Ray job from KubeRay to scale out to thousands of ephemeral Ray clusters. And then this way, we can actually shard the data set across thousands of Ray jobs and then automatically retry like individual Ray jobs if they fail for whatever reason. This is the example Ray job from our experimentation. We used the Ray runtime to configure like which prefix of the data set to process. This example also shows Python dependencies, but in our actual testing, we just like baked all the dependencies in the image because downloading the Python dependencies thousands of times would not be ideal. And so due to the way the data set is structured, it's actually fairly easy to shard it out across multiple thousands of Ray jobs. We basically just give each Ray job a point in the grid system, and then the Ray job then walks through every file and image of that in that path, and then does the torch transformations. So some numbers. If we basically shard the data set for each grid point, that actually ends up being about 22,000 Ray jobs. assuming each ray job runs a ray cluster with 1 ray head, 10 workers, each with 4 CPUs and 16 gigabytes of memory, the total capacity we need to process the entire data set would be almost 1 million CPUs and about 3.5 terabytes of memory. In our testing, we used a GKE cluster with 10,000 E2 standard 4 nodes. So that's about 40,000 CPUs and 160 terabytes of memory. If we attempted to run all the ray jobs at once, we would actually run into various scheduling issues, since like some ray clusters would be left unschedulable, like the ray head or like several workers wouldn't actually be scheduled, and then a bunch of jobs would be stuck and the actual data processing job would never finish. One naive approach and simple way to solve this is we could just use like significantly larger instances, right? So for example, if you ran 10,000 N2 standard 96 nodes, we would actually have just the right amount of capacity, like the 960,000 CPUs, to run all the ray jobs at once. However, that's obviously significantly more expensive and not the most cost-efficient solution. And so to solve this capacity problem, we leverage Kueue. So Kueue is a Kubernetes native job queuing system. It ensures that jobs that don't fit the existing capacity should wait, and it ensures proper execution of jobs by their priority order. And so with Kueue, we can kind of just deploy all the ray jobs at once and rely on Kueue to run a subset of the ray jobs as capacity becomes available as jobs are kind of finishing. Kueue also has native integration with ray job and ray cluster. It inspects the resource requirements of the head and worker pods and ensures the resources are accurately represented in the cluster queue, where we specify the available quotas available for this cluster. And yeah, you can see in the slide the example cluster queue that represents the total 40,000 CPUs and 160,000 gigabytes of memory. Yeah, so let's look at some graphs. So this is just the graph of number of nodes. It takes a few minutes, about like 10 minutes for GKE to kind of stabilize on the 10,000 nodes. Next, we have like the KubeRay object count in the GKE cluster. You can see like once the GKE cluster has stabilized on 10,000 nodes, we then deploy the 22,000 ray jobs we created. And then you'll note that KubeRay doesn't like immediately create the 22,000 clusters for the 22,000 ray jobs. That's because Kueue will basically suspend every ray job on creation, and then as capacity is available, it'll allow some ray jobs to resume. And so the number of ray clusters you see sitting around like 1,000 is capped based on the amount of quota available. So at any point, you'll have only 1,000 ray clusters running, even though the cluster has like 22,000 ray jobs that are kind of trying to complete at once. And this approach is also like very popular for when you have like a GPU workload, a workload that needs GPUs. You can basically do proper gang scheduling of GPUs and priority scheduling and all those advanced use cases. Next, we have like the work queue depth. These are more like Kubernetes controller metrics. The first graph shows like the initial object ingestion when we created the 22,000 ray jobs. Then you see the red line at the bottom. That's the ray cluster work queue depth. So similar to the last graph, we see big spike in ray jobs, and then as Kueue allows capacity, we see the work queue depth of ray clusters kind of gradually increasing. Same with the reconcile rate, big spike in ray jobs, and then it kind of decreases as the number of ray jobs are kind of gradually completing throughout the job. The final graph here is just the KubeRay memory and CPU. You can see the KubeRay is fairly resource efficient and lightweight, considering it's managing like tens of thousands of ray jobs and tens of thousands of pods at any given time. It's only using like 4 CPUs and like 8 gigabytes of RAM. Really, the only optimization we had to make in KubeRay was increasing the reconcile concurrency because it defaults to 1. And we just had to make sure that there was sufficient memory. And then the reason why you see multiple lines is because we run KubeRay with HA configuration so that if any KubeRay dies, another one can immediately take over. And then the final piece of the puzzle that I haven't covered yet that made all the difference is fast data access with GCS Fuse. And Saikat will kind of cover that in more details.
Okay, so I'm going to introduce CSI drivers in Kubernetes, and then GKE GCS Fuse CSI driver that we built ground up to make it work seamlessly to mount GCS buckets on Kubernetes clusters. So CSI is a Kubernetes standard specification of how you can make storage available to Kubernetes pods as mounted volumes. And GKE GCS Fuse CSI driver is an extension of that, specifically focused on mounting GCS buckets. So what are some of the benefits of the CSI driver? So the first thing that I would like to point out is portability. So you get POSIX-like file system. I say POSIX-like because it's not fully POSIX compliant, but you get the most of the POSIX compliance. And that means it's also compatible with any file system APIs and also the Ray data APIs. Reliability is a big part when you want to deploy things in production. We completely control the upgrades of the GKE CSI driver to address vulnerability fixes, bug fixes, new features. But at the same time, we need to ensure that these kind of upgrades do not impact the user pods or the Ray pods, for example, and they should not take a downtime. And from the security standpoint, we have fine-grained integration with workload identity federation. So you can set up access control rules like this Kubernetes namespace of this service account has access to read and write buckets. So all of that is baked into the volume APIs of Kubernetes. What else? So we also ensure that you don't need to use privileged pods to mount the buckets, because that's important so that you don't need to give unnecessary elevated privileges to your user pods. Observability is a big one where if you want to deep dive into performance bottlenecks, we want to have native Prometheus compatible matrix, and that you can slice and dice by pod and namespaces. And scale is something we have been iterating a lot over the past 1 year because of the growing demands of the workloads that we are seeing in the order of thousands of nodes and tens of thousands of pods. Some of the improvements that I would like to highlight that we did in our CSI drivers are in the control plane of the CSI driver, we identified bottlenecks like chattiness between the driver and the Kube API server. So fixed all of those, ensured that we don't consume unnecessary quota. And on the data path side, the core GCS Fuse process, we optimized heavily to ensure that it works for both the small files use case and the large file use case. The small file use case could be, say you have a bucket with millions of objects that need to be read into your Ray train job or something like that. So metadata can become a bottleneck there, so we implemented some advanced caching strategies inside GCS Fuse. And on the larger file spectrum, like Parquet files, which packs a lot of training data samples, or model weight files, we have implemented features like file cache and parallel prefetch. So what it does is GCS Fuse will seamlessly take advantage of any available local SSDs on your GKE nodes. And when the user applications triggers reads on these large files, GCS Fuse will asynchronously start pulling in those chunks of sub-chunks of the large file in parallel into the local SSD, and subsequent reads of the blocks of that big file will be served directly from the local SSD via GCS Fuse. So these are some of the advantages. Now, to tie the GKE CSI with the Ray ecosystem, I'm going to show a short demo of a Ray train job where we use GKE GCS CSI driver to run a distributed training with 500,000 image files and using Ray train and PyTorch Lightning. So this is how the volume spec looks like for a Ray cluster. You can see here we support like volume APIs like CSI, ephemeral, and persistent volume. And it's very seamless to integrate into the Ray cluster spec. And now for the specific demo that I'm going to talk about, so what we have here is a GKE cluster of 1,000 nodes with a queue deployed. So we have 2 local queues. This could be, like you could segregate it by teams or namespaces. So we have 2 local queues. We are going to deploy simultaneously 4 ray-trained jobs. Each of these ray-trained jobs triggers creation of ephemeral ray clusters. And each of the ray cluster has around 250 ray-trained pods. So in aggregate, there are 1,000 pods that are admitted into the cluster. And all of these pods are directly reading from the GCS bucket through the GCS, like the GKE CSI driver. And in the bucket, we have a few artifacts. So we have the pre-trained model checkpoints that could be used as a starting point to bootstrap your the training experiment. You have the training dataset that contains those 500,000 image files. And you have the experiment output artifacts. So basically, as you progress through your epochs, you could write back checkpoints back to the same GCS bucket. And drilling down a bit further, if I double-click into each ray pod, you can see that there is a GCS Fuse sidecar container that is automatically injected by GKE because you specified GCS volumes in your pod spec. And below, you can see there is something called a secondary boot disk, where we basically bake in the ray container images, because these are very large images. And they are pulled into the GKE node in a streaming fashion, which results in very fast pod startup time. And this is the video that I have. I'm going to. This is a short demo on how to deploy multiple. And let me fast forward to the actual training run, because I've already talked about the introductory part of how the setup is done. Demo now. So we have the GKE cluster set up with 1,000 nodes with the ray images cached in the secondary boot disk attached to the nodes. And the GCS bucket, we can see the data set and the pre-trained checkpoint. Now we are going to admit the first ray job to the cluster queue, and this will spin up a 250 pod ray cluster with 1 ray head node and 249 worker nodes. And we will also take a look at the ray job. It's showing as an initializing state. From the ray dashboard, we can now see that the job has started, and eventually we should see 250 ray trained workers also started. We are now spinning up 3 more ray jobs, each of which would spin up 250 more pods, so an aggregate of 1,000 pods running in the cluster simultaneously. And all of the ray jobs are now in initializing state, and one is in running as shown before. We'll set up a watch just to monitor the progress of all the ray jobs. And we can fast forward when the job completes and take a look at one of the jobs, ResNet 4, as to why it took slightly longer time to complete. When we see the ray job logs, we can see that there was a exception due to failure to initialize the process group, because of which the ray job restarted gracefully. And once it restarted, it initialized the ray workers and also resumed its training from the known location of the checkpoints. And eventually the ray train epoch would complete in around 88 seconds. And the job wrote back the result back to its job specific directory. So as you can see here, there are 4 job-specific directories with the output artifacts. We'll also quickly take a look at the observability of the bucket to see various metrics like the read, list, get, request counts, and the egress data over the network. Similarly, the CSI, the GCS Fuse CSI driver also emits matrix which can be sliced and diced by various fields like pod name, namespaces, and we also emit various GCS Fuse specific matrix as shown here. Yeah, so this is the demo that I had where what I tried to show is like you can deploy multiple Ray jobs, each reading from GCS bucket seamlessly. You could even like mount subpaths within your buckets if you have a huge bucket with data sets for multiple teams. So there's a lot of flexibility and also configuration knobs for your that is attuned to your dataset shapes. It could be a bunch of small files. It could be a collection of large files. We try to cover both the end of the spectrum. And going back to, so we have some information provided here to try out the GKE managed KubeRay operator, and we also have the GKE GCS Fuse CSI driver that can be easily enabled on a GKE cluster. It's enabled by default on GKE Autopilot, and it can be enabled through gcloud console and Terraform on the CSI driver. Sorry, on the standard GKE standard clusters. And yeah, try it out on GKE. We have uploaded all the code base to the KubeRay perf tests. Thank you. Any questions? Yeah.
So when scaling a GKE cluster to like 15,000 nodes, any best practices or things to watch out for?
Andrew, you want to take that?
Yeah, I think definitely doing it gradually is going to kind of help kick up like our systems to like scale up to the traffic. I think the biggest kind of gotchas that we see is at really large scale. It's really easy to deploy controllers or daemon set in the cluster that make really expensive API calls. So like the most common example we see is you deploy a daemon set. The daemon set needs to look up the node information about itself. But the way it does that is like it lists every node, and then it uses like a field selector to find the node that matches itself. But then if you do that at 15,000 scale, you have 15,000 processes like listing 15,000 nodes. So like I think the larger your GKE cluster becomes and the more pods and nodes you run, you have to be a little bit more careful about the type of clients that are going to be deployed in the cluster and making those type of requests.
Well, OK, so when you're starting nodes, probably kubelets have to make some list requests. So is that process
yeah, so
GKE
is like, when we do our scale testing, we are very, like we take into account the kubelet traffic, because kubelet is like the most high volume traffic client, right? So in all our benchmarks, we're basically ensuring that kubelet is behaving well. And we've also done, SigNode, a bunch of people from Google have kind of done a lot of investment into making like node scalable. Like one example is we split out the node heartbeat into the lease API instead of doing it in the node API. And that kind of improves scalability of the kubelet quite a bit.
Cool, thanks.
And I can add a couple of points there. Another thing that you need to be aware of is the quotas that you have in your project. You could hit quota limits and cause retry and back off. And that's something to watch out for, that we have hit a lot in trying to scale at that numbers.
Another hack I'll mention maybe just for this group is if you are planning to actually run 15,000 nodes, maybe open a support ticket as well and just let Google know that you're going to do that.
Good point.
All right, so I had a few questions. The first one was, well, one other thing that Ray offers is any scale on raw Google Cloud. When would you recommend using GKE versus just raw Google Cloud?
Yeah, I think, well, like that was a kind of like a newly announced thing at Ray Summit. I think, you know, customers that really care about fully open source solutions, really flexible, customizable deployments that are kind of portable across any kind of Kubernetes cluster, that's kind of generally where we would recommend KubeRay. But I think, you know, as we saw in the keynotes and many other talks, if, you know, any scale has, you know, really valuable proprietary features that you want, we're partnering with them as well to make sure that any scale on GKE is also going to scale really well and work well on GKE.
Thanks. Another question is for that large job, data processing job you were showing. In the end, it was queued on Kubernetes side, and you had separate jobs. At that point, what value Ray is adding? Because if you just use normal Kubernetes jobs, put them on the queue, and you know the pods can discover themselves.
Well, I mean the main benefit is Ray providing the libraries for that distributed computing.
The thing is, you're putting the dependencies in the Docker too, right?
Sorry, what was that?
So you put the dependencies in the Docker as well, and you just read the range from the bucket and process it and write back. So what's Ray adding there?
So if the question is like, why did we use Ray for the use case?
Yeah, if you just you know, put an entry point in a Kubernetes
I think to put it simply, like Ray data is a great solution for really scalable like data processing, and very popular to use Ray data on Kubernetes, right? Because Ray, in the end of the day, Ray needs to run on some sort of compute, right? As magical as Ray feels sometimes, to like ray.remote and it just runs. At the end of the day, like it does need to run on something, and obviously, like you know, Ray on Kubernetes, one popular option because you know Kubernetes kind of provides that scalable compute for Ray. So that's kind of where we're coming from.
Okay, and the last question: let's say whatever code I implemented, it's not good enough to run on a very large cluster. Let's say the daemon set example. For some reason, the cluster I've deployed. And I would need more than one cluster. So if I would want to submit jobs, then I would need, as a developer, need to select what queue to send to, or do you offer anything to like have like a unified queue?
Yeah, so Kueue basically supports multiple cluster queues, and the way you manage what queues your jobs land on is using one of the supported labels that come with Kueue. So you basically annotate the Ray job with the label that matches the queue name. And then that'll basically place it on one of the available cluster keys.
Okay, thank you.
Yeah, last question. Yeah.
Hi. I had a question in the context of a very large training job. So the approach you described before by splitting up it and a multiple Ray job that you schedule with Kueue, would it work out? I mean, would you have any advice to use a similar approach in a context of a large data parallel job, given that if one failed, well, because of the gradient sharing, you would have to restart everything. Is there like any tips or something you would notice that would be best to use in that case?
I didn't fully get the last part of your question. It was inaudible.
Oh, sorry. Which part?
You were mentioning about, are you talking about sharding strategies?
Yeah, I mean, if you have a very large training job that you would like to split the maximum of nodes possible, would you still advise to use this approach of dividing in multiple?
Yeah. So typically, I think I can talk purely from the GCS Fuse CSI perspective. It's better to have like a one pod schedule per node and consume all your accelerators, because what will happen under the hood is we attach a GCS Fuse sidecar on every pod. Now if you deploy, let's say you have a node with 8 accelerators, 8 GPUs, and you deploy 8 pods to consume them, you will get a GCS Fuse instance for every pod, and you will not be sharing like the caches. So that, and you will get significant benefit if you have a cache sharing. So it's better to have one pod to consume all accelerators rather than have each pod consume like one accelerator each. So that's one best practices pattern I can recommend.
Okay, thank you.